So we have medium problem. Given some number n, we want to find how many numbers in 0 up to n has some properties, and this properties is about custom rule about digits. So imagine our number is one like 2, 5, 4, and we have some properties where we can convert 2 to 5, 5 to 2, and 4 is forbidden. So we have properties for all possible numbers. Let's write all the properties. So this is symmetrical. It converts 1, 0, 8 converts to 1, 0 converts to 8, 0 to 0, 3 forbidden, 4 forbidden, 7 forbidden, and this numbers 2 converts to 5, 5 converts to 2, 6 to 9, and 9 to 6 gives us like mirror rule, and we want to find if we apply this mirror rule to all this range of 0 up to some number, how many of them became different if allowed from initial. For example, 8, 8 converts to 8, 8, and it's not different, so it doesn't count. But 8, 9 converts to 8, 6, and it's accepted. So this is a simple brute forceable solution, because even our numbers is 10 to the power of 4. Analyzing each number individually takes just logarithm of its value. So even we have like 9999, the biggest number of 10 to the power of 4. It only 4 digits, and we can analyze them in a busy loop, like 4 x in 0 up to n. Just analyze and say if it's accepted. Now let's look at the solution. So this was my accepted solution. I just made it very clear, very simple and stupid. Just check each, convert to string and check each digit. Nothing special. But now let's look at the goal fit implementation. So yep, this is the shortest one. So I use regex, the same count, but this is a regex, and same regex is accepted. You have to use this starting and ending to use in operator, and then you take this, you have any prefix, any suffix, and you have to have at least one digit from 2, 5, 6, 9. So this is how it translates to English. And now I will show you this solution. This is a Rust solution, and I would publish it. Now let's look at it. It's kind of scary and crazy, and I wouldn't write it myself because I don't have a good theory in my mind for that, but with help of some our robots I could write it. So Thank you for your service. Now let's look what does it mean. I will try to explain. So this is logarithmic solution. Logarithm 10 and solution. Okay, so this solution is based on so-called digit dp. This is a term for that, digits dp. Imagine we have some number 8, 5, 4, 9, 9, like this. This is our n. Now, when we iterate in, we can consider combinations. This is combinatoric based combinations. For the digit 8, we have 1, 2, 3, 4 leftover digits. So this is our combinatorics, 8 and 4 digits of tail. And what if we say that our 8 is actually a tree of all numbers starts with 0, then from 1, from 2, from 3, from 4, 5, 6, 7, and the final 8. So this is a starting point, and each of them has the suffix of 4 leftover digits to analyze. And we can say that each this tree maintains a is itself a subtree of all digits starting with so this would be a range from 0 up to 9, 9, so 4 nines. Okay, and this is 1. It is from 1 and 4 zeros up to 1, 9 and 4 nines. So this is a subtrees. And we could say that some of these subtrees has forbidden prefix. For example, we don't allow this 4, so this is forbidden subtree. We don't allow 7, so this is also forbidden. Now, what about the subtree that starts with 2, for example? This is a very good and lucky subtree, because 2 already gives us some property of all these numbers in this range, because as all of them has 2 in the start, that means 2 converts to 5, and our mirror property is, yes, mirror rule is like accepted for all this subtree. The same for subtree starting with 5 and 6. This is a good, I would say, let's mark it with some mark. 5, 6. This I go 5 to 2 and 6 to 9. This is converter. So can we say how many numbers in this range? So this is very simple. It's like 10,000, I would say. Yes, 10,000. But let's also talk about other numbers like 0. 0 is doesn't have mirror rule in them, so it's still not very obvious how many of them are in a good condition. But let's look at this problem in another way. So we have all these numbers. What if we say that we have two numbers starting with 2, 5, 6, yes, 6, and they are good, and they have the length of the tail equal 4 length, and the count of them is 3, so it's 3 to the power of k unique combinations. Yep, am I right? No, I'm not right. This is not correct way of intuition, but let's backtrack from this. Let's talk about the forbidden numbers. Yes, the forbidden numbers are 1, 2, 3, 3. What are them? 4 and 7. We have 3 forbidden numbers. That means in a range of 0 up to 9999, we have some numbers with length up to k that are forbidden, and this is combinatorics. So from 0 up to 4 nines we have 3 to the power of 4 forbidden combinations of 3, 4, and 7. Again, this is again not correct way of thinking. Let's forget about it. Maybe I should start with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 1, 2, 3, 4, 5, 6, 7. 7 to the power of k. This is the combinations of all possible permutations, okay, combinations of these numbers in a range 0 up to the 10 to the power of k minus 1. So okay, this is all, and from them we have some number that has property of mirror, like 0, 1, and 8. I have 3 numbers to the power of k that are require to have some other some numbers of 2, 5, and 6, and 9. So if we have prefix like this 8, for example, starting with 8 and 4 digits with suffix, the range or total combinations is 7 to the power of 4 for the 4 digits, where we have all these numbers, minus 3 to the power of 4 of combinations that consist only of these numbers 0, 1 and 8, because if we have all ones, like 4 ones, this gives us forbidden number, because it doesn't convert, it does convert to itself. So this is how it looks for the 8. But if we have suffix with 2, that means we have already mirror rule for the 2 converted to 5, and that means we have just 7 to the power of 4 numbers that are consisting of all the possible 7 digits permutating in the 4 positions. So this is how we judge our prefix and suffix. And that means if we have, so our initial 85499, let's return 85499. So for the 8, we going and analyzing our subtree, starting with 8 gives us 7 to the power of 4 minus 3 to the power of 4. Then start from 7. 7 is forbidden. Let's skip it. 6 again. 6 converts to 9, then it's just 7 to the power of 4. Then 5, 7 to the power of 4. 4 forbidden. 3 is forbidden. 2, 7 to the power of 4. 1, 7 to the power of 4 minus 3 to the power of 4, and 0 the same. So if you with me, this was my intuition about how we checking how many good digits or good numbers we have in some suffix. So for example, if we're starting with 2, we're starting with 2 and 4 zeros, ending with 29999, and inside of them we have 7 to the power of 4 numbers consisting of these digits 0, 1, 2, 5, 6, 8, 9. So basically this is from the suffix of 8, but for the 8 we shouldn't take 8, because the 8 has 8 0 0 0 0 up to 8 9 9 9, and it is bigger than 8 5 4 9 9. So the 8 is skipped, we don't take it. However, we say that the next 5 has the prefix of 8, and that means if the previous prefix has applied mirror rule to them, so if the previous digit, any previous digit in the prefix has numbers like 2 5 6 9, that means we don't have to subtract this 3 combinations, because we don't have to use 2, 5, 6, 9. We can use all 7 digits. So I hope I explained it. So now the 5s gives us 5, so 5, 4, 9, 9, 5, 4, 9, 9. This was 8. For the 5 we go 4 is forbidden, 3 is forbidden, 2 2xxx, it is 7 to the power of 3, and we don't subtract because 2 is a mirror accepted. Now 1 is 7 to the power of 3 minus 3 to the power of 3, and 0 the same. This is how many numbers we have in this range, and we have prefix of 8, 5. And now we are at 4, and 4 is forbidden, but we still can have numbers like 2, so 8, 5, 2, and then some prefix of xx. So this is 7 to the power of 2, and 1, 7 to the power of 2 minus 3 to the power of 2, and 0, 7 to the power of 2 minus 3 to the power of 2. Okay. And after that, we can't have prefix with 4 because 4 is forbidden and any continuation will be forbidden. So we are returning our result. Now let's look at the code again. So this is pre-computations of 7 power and 3 power. This is a current digit, and we iterating over from 0 to current digit. We skipping, this is a bit mask, by the way. We're skipping the digits that are forbidden is 3, 4, and 7. And this is a bit mask for the bitwise positions of these bits, and we checking if the current digit or the previous bit prefix has seen the digit that are perfectly mirrored to another digit and not to itself. And if it is, then we don't subtract, and if it's not, we subtract 3 to the power of the tail length. And if we met the digit that are forbidden, we return early. And after that, after entire loop, we have to do +1 if the number itself is not forbidden. So I would explain the final +1. So imagine we have, instead of 4, we have some good numbers. So 8, 5, 9, 9, 9. So we explore it from 0 up to 7, from 0 up to 4, 0 up to 8, 0 up to 8. But we taken this number itself as a prefix, and we don't consider it. So 8 we don't consider it. We are not haven't explored this last digits. So after the loop we have this as prefix, and if it's okay we are counting it, so count plus 1 if it's okay. So this is solution. I think I explained it. I hope I myself understand it. I would say I will understand it to describe it, but maybe not very deep understanding to write this myself without some hints. So that's it for today.